Hi guys, and welcome back to term 3. Okay, in this particular section of work, what we're going to be doing is moving on from the work that we basically finished up at the end of that session during the term break, and we're moving on to having a look at further applications of differentiation. For a start, to this section on sketching polynomials. Now what I've done here is I've decided to put some material for these next parts of the work up onto OneNote here, which is something which from memory I have shared with you, but I will just check on that a little bit later, and if not I will share it with you again. So in here there's a brief notes and also the exercises that I want you to complete. The text reference, as I say, a few notes here as well, and I'm going to put a couple of links to a couple of examples. The first will be this one that I'm doing right now. Okay, and then the next section on parametric equations and the ones after that will also be listed here. Okay, so polynomials, let's have a look at that. Alright, so I'm going to use a combination of writing on the screen, and also we might have a look at some stuff with Graphmatica just to confirm what the graph looks like. Okay, so let's begin. Okay, so here I've got a function. This is called a quintic. It's a power of 5 function. This is an example of a polynomial, basically because it consists of different terms here, all of which are basically a number times a variable, and that variable might be to a power, and like here, although with 16 you can still count that as being x to the power of 0, of course. Okay, and so this is an example of a polynomial. It's also given in factorized form here, and this is actually question number 302 from your workbook that I'm going to work through with you. So what you're asked to do is basically to sketch this function, and what we need to do is we need to have a look at finding the following. The y-intercept is going to be needed to accurately graph this. The x-intercepts, any maximum points, any minimum points, and any points of inflection. Now for some of this we will use calculus, but for the y-intercept and x-intercept we're just going to use straight algebra to do that. So let's begin with, for a start, the y-intercept, which is usually quite easy to find. Now the y-intercept is where it's going to cut this y-axis over here. Now if you think about that, that's when x is equal to 0. So we simply let x equal 0 and then find out what the y value is. Now that top equation there is the easiest one to use, because if you make x 0 here, here, and here, and here, all those terms become 0 and we're left with 16. So our y-intercept as a point is the point 0, 16. Okay, let's have a look at the x-intercepts. Once again, this will be where it cuts now the x-axis. Now for this function here, we might better see from that factorized form that it will cut actually at 3 different points. And when will that occur? Well, at any point where it say cuts an x-axis, okay, so if I just draw a rough sketch here, this point, which might be, say, I don't know, 3, but it'll be 3 zeros, the y value is 0, and any other y-intercepts, x-intercepts, it'll be also when the y value is 0. So this gives us a method of finding the x-intercepts we're going to let y equals 0 and solve that equation. Let's get rid of that. Okay, so that means we're going to have to solve the equation when y is 0. Now this form here is the much easier one to use because all the work really has been done for us. Now that it's in factorized form, we simply need to find out when each of those factors is equal to 0. Notice we have a triple repeated factor here. Well, that will occur when x equals 1, because 1 makes that bracket 0, and 0 times the other brackets will still be 0. Another value will be when x is equal to positive 2, because that bracket will become 0. So something times 0 times something is still 0, and also when x equals negative 2 for similar reasons, because it makes that bracket 0. So we have these x-intercepts if I write them as points. That's all good. Now let's have a look at trying to now find these other things here, the maximum, minimum, and points of inflection. Okay, now to do any of that we're going to use some calculus now. Okay, and for max min points, which you might recall from the work we did during the holiday session, these are called stationary points. They are points where the gradient is equal to 0, and hopefully we've got the idea now that the derivative tells us the gradient at any point, so we want to find out when the gradient is equal to 0. Now the other time that you get the gradient being equal to 0 is when you have horizontal points of inflection. And what are they again? They're sort of points that may look, say, something like this, where if you look at that point right there, and if I drew it better, but the gradient at that point is also 0, and this is known as a point of inflection, where the concavity, also an idea discussed in the holidays, this is concave down, this part here, and then it changes to concave up. Okay, so points of inflection are where the concavity changes. So we have that here for this horizontal one. Okay, so let's find our first derivative, because we can use that to get our maximum, minimum, and perhaps any horizontal points of inflection as well. Okay, so let's make a bit of room, say here. So we've got this function. I will just rewrite it out. And the derivative now, since it's simply a whole lot of different power terms, we can derive each of them separately, just using the power rule. And now we need to find out when that is equal to 0. Now there's absolutely no reason at all that we can't actually find out when that is equal to 0 using our calculator. One thing that you might notice though that will give us a point straight away is that there is a common factor of x throughout here. So I will in fact do a little bit of manual work there. And then to find out when this part equals 0, I plug that into my graphics calculator. And so the different points of where the derivative is equal to 0 is when x is equal to 0. That comes from when this factor is 0, the whole thing will be 0. And then finding the solutions for this part here actually gave me two other answers, 1.6 and -2. Now notice that negative 2 was already a point over here. This was a x-intercept. So this x-intercept is either going to be a maximum or minimum point, or possibly a horizontal point of inflection. Okay, so let's get the y values for each of these x values, because we need to be able to plot the points. Now be careful here, we've got our original function and we've got our derived function. For these x values, if I want to plot them on the graph, I need to use the original function, this one here, okay, to get the y values. So by doing that, I've got these y values. 16, notice this is already a point we've already got again. Negative 11.2, that was obtained by putting 1.6. I actually use this function here to calculate the y value, and for negative 2 we have 0. So we have these points which are going to be either maximum, minimum, or horizontal points of inflection. Okay, so how do we distinguish? Well, what I'm going to use is the second derivative test to allow me to do this. So let's get the second derivative. This notation here, y double dash, is when you are deriving for a second time using Newton's notation for derivatives. So taking our first derivative and deriving it again, we're going to get 20x cubed plus 36x squared minus 24x minus 32. Now we are going to substitute these different x values into our second derivative. So if x is equal to 0, let's have a look at the sign of our second derivative. So putting 0 in throughout here, we're going to get negative 32. In other words, it's less than 0. And that's all we need to know, because that tells us that this point, 0, 16, is a maximum. And once again, that work came from the holiday session. And if x is equal to 1.6, the second derivative, now putting that throughout here, I got a value greater than 0, and you can check on that. Okay, but yeah, it does come out to be greater than 0, and therefore that tells me that the point 1.6, negative 11.2, is a minimum point. And if I let x is equal to negative 2, okay, putting negative 2 throughout here, the second derivative actually came out to equal 0. Now that might be pointing to this being a horizontal point of inflection, because we know it's a turning point, or it is a stationary point, I should say. But you've got to be a little bit careful when you have an x value where for that x value the first derivative is equal to 0 and also the second derivative is equal to 0. It may be pointing to a horizontal point of inflection, but there is situations of test failure, which I'll have a look at an example in class with you. So just to be absolutely sure, what I also did was to draw up a little table. This is the kind of table that we used of trying to determine whether points are maximum or minimum before we use the second derivative test. Now I've taken the x value equal to negative 2. The first derivative is 0, so it's flat. Now I put negative 3 into the first derivative here, okay, and it came out to be positive. I took an x value slightly greater than negative 2, such as negative 1, and I put that into this first derivative, and it also came out to be positive. So what we've got is we've got positive gradient, flat, and then positive. Now this is therefore a horizontal point of inflection. Okay, so what do we do with all of that? Well, we're going to plot those values onto our graph. Now just change that to a different color. Now we've got points such as 1, 0, 2, 0, negative 2, 0. These other points over here, also the x values, if you look at them, are not that far away from these. The maximum y value we need to be going up to is 16, and we're going down to negative 11.2. So just to spread this out a bit, I'm going to make that x equal 1 there and 2 there. Could possibly have spread that out even a little bit more. So negative 2 there, and I'm going to make 16 there. Now you do not need to use the same scale on both axes, and I'm going to make that pretty close to negative 11.2. Let's make that negative 12. Okay, and let's now plot some points, and just change the color to something else again. So negative, these x-intercepts, let's plot those. So 1, 0, that's a point there. 2, 0, and negative 2, 0. 0, 16, and now let's get these other points here. 1.6, negative 11.2. So 1.6 would be roughly there, negative 11.2. Let's say that's pretty close enough to it. And I'm just going to right next to that the actual point. Now, what else do we know? Well, we know that 0, when x is 0, in other words 0, 16 is a maximum. So on my graph, I'm going to just very roughly make that a maximum kind of point. 1.6, negative 11.2 was a minimum. So it's going to go down then back up there. And this point, negative 2, 0, was a horizontal point of inflection. So it was positive gradient after that point, positive gradient before that point. Okay, so I think the graph's going to come up here, through there, down through here, turn here, and come back up there. So let's sketch that in. Always a good idea to do this in pencil. And it's a bit harder on this graphics tablet that I'm using. And I prefer just to draw in some dashed points there to help me. Okay, so let's see if I can go over this. This is becoming quite difficult to do on this tablet. Okay, it's not too bad, but messy in this region here, so let's retry that. Okay, that will do. I would be still not happy with that, but that'll have to do. Alright, so that I think is the graph of that, and what you can do, and I'll leave this as an exercise for you to do, you can graph this on your graphics calculator. And when I did this on Graphmatica, I certainly got a graph looking like this one here. Okay, the only other thing that we might have to find is non-horizontal points of inflection. Now I know there's a point of inflection here because I've already found it, and that's a horizontal one. But what about other points of inflection? So let me just go and highlight this point here again. This is a point where the concavity changed, but there's also a point around about here where the concavity also changed. So this is concave down, and then it becomes concave up after that. So how do we find out that point? Well, this is a non-horizontal point of inflection. So how do we find that? Well, what we have to find is when the second derivative is equal to 0. Okay, now we've got one point here where it's equal to 0, but there should be another point also here. Alright, so guys, up here in the top right hand corner you see that I've done a little bit of work here, and there was one thing I must admit, I'm being a little bit inaccurate with this point here. So I found out when the second derivative is equal to 0. Now one answer is -2 as expected, but these other values here, let's just go over what they are meaning again. So -0.8, so round about here, this is something I should have picked up earlier. This is another point of inflection, -0.8. Just tidy that up a bit. Yes, this is basically concave up and then changing to concave down here. So yeah, this is another non-horizontal point of inflection, and this point here is, no, that's inaccurate. According to the calculation here at 1, this is where it changes from concave down to concave up, and that actually from the graph does look about right as well. So we've got 3 points of inflection, -2, 0, when x is -0.8, and when x is equal to 1, y is 0, because that's a x-intercept. Now for -0.8, we'll need to go and put that into our original function here to get the exact, sorry, this point here, the exact y value. Okay, so I've done a little bit of calculator work, and what I've found is that for me, when I'm putting 0.8 into here, here and here, I'm getting a y value of round about 8.7, which, looking at our graph, given that this is 16 here, this is about right. Okay, so this is 8.7. Okay, so -0.8, 8.7 is that the point of inflection there. Okay, so guys, with this then, you'll need to set your working out something like this. I know it's a lot of work, but if you get a question like this in the NCA exam, you will need to demonstrate your use of calculus as well as some algebra here, and come up with a good hand-drawn sketch, okay, even though you might be able to reproduce that on your calculator as well. Okay, see you in class, and we'll have a look at a further example as well.